In this section of the course, we'll look at parametric equations that are defined in terms of trigonometric functions. Okay, so in the very first example, we have x defined in terms of sine of t plus 2 and y is cos of t minus 3. Now, we didn't bound any value. The question hasn't bounded the value of t. T can take any real value. Okay, we were asked to show that the Cartesian equation of the curve is given by so. That looks like an equation of circle. So let's see how we can define the Cartesian equation. We said previously that we would make t the subject of the first equation substituted into the second equation. But that in this case, that strategy when we have trigonometric functions is not going to work. So we're going to come up with some other plan. We can rearrange the first equation up to a point where sine of t equals to x minus 2, and we can use our very famous identity that 1 equals to sine square of any angle, in our case t here, plus cos square of that angle there. So we are saying that x minus 2 in our case is equal to sine of t, and our y value is cos of t minus 3. So how can we go ahead and use the this equation, the famous identity that I'm putting in a rectangle here? We can square both sides of this equation, so we'll have sine square t equal to x minus 2 square, and we can have y plus 3 equating to that to cos t, and squaring both sides of that equation will give us y plus 3 squared. Now, putting sine square of t plus cos square of t, equating that to 1, we can write x minus 2 square plus y plus 3 square is equals to 1, and that is exactly this equation here. So we found that by the equation over here, this famous trigonometric identity. Now we were asked to sketch the curve of this curve here. Now we know that this is equation of a circle with the radius squared being equal to 1. So taking square root of 1 there, we still going to get a radius of 1, and the center of our circle is going to have 2 and minus 3 coordinate. So this is the coordinate of the center, which is, if we take point 2 to be there and point minus 3 to be here, and we put the dot here for the center, and dividing that proportionally, we will have some sort of a circle right here. My drawing isn't perfect, but I'll show you on the next slide what's the perfect drawing going to look like. Okay, as I promised you, here's the graph of the circle there. And then with the next example, our x and y are both defined in terms of sine. So the question is asking us to find the Cartesian equation in the form y equals to f of x. So we have to eliminate t somehow and define what's the values of x that e can take. In other words, state the value of k. So in part B, we will look at the range of the value, the function f of x. So x is sine of t, and y is double angle here. So y is 2t. We can use the double angle formula for y, which is 2 lots of sine cos t, and we can substitute this value of x where sine of t is, and write cos of t as the square root of 1 minus x squared, because cos of t is simply the square root of 1 minus sine squared, as we did in the earlier exercise preliminary questions that we went through. I showed you that rearranging equation 1 there we had 1 equals to cos square of t plus sine square of t, and if we make sine the subject of this formula, we can, or rather cos the subject of this formula, we will have cos defined as cos of t will be defined as square root of 1 minus sine square of t. So we're going to substitute that x for sine of t, and we will have, and what will we get is y equals to, if I can get my pen to function, y equals to 2x, and replacing this cos t with that expression there, we will have the square root of 1 minus x squared. Okay, so let's see what the constant value of k are. So we know that we cannot have any negative values under the square root. Therefore, 1 minus x squared must be strictly positive. Well, it can be equal to 0 as well, but that means that x squared must be always bigger than 1, and x value is bounded between -1 and +1 there. Therefore, value of k must be 1 for our function, our square root function to work properly. Okay? Okay, here's another reason yet why x has to be bounded between -1 and +1. If we consider the values of t that we were given in our function at the beginning, x is sine of t, and the sine curve between 90 degrees and minus 90 degrees will have reached its maximum minimum, which is -1 and +1. And sine curve in any case doesn't have a range any larger than 1 and -1. Therefore, that's why the values of x are bounded by -1 and positive. Now, in part B of the question, we are asked to calculate what's the y value, what's the range of y. So in our case, um, well, if we substitute 1 into under the square root, we will have a 0 under the square root, and 2 times 1 times 0 will still be 0. And so the boundaries of x, actually, the highest and lowest value of x will give us y value of 0. So surely y will have a larger value. So let's look at the definition of y in terms of t. So we're gonna consider this range of values for t and explore how sine of 2t behaves. We know that double angle, the multiplier of 2 inside the bracket, means that we will have two, well, we have a stretch factor of 2, so it will squash the graph and make it steeper. It will so we will have a graph that will look like so over the period of negative pi over 2 and positive pi over 2. We will have one full period of sine curve, or rather negative sine curve, uh, and then so it will, again, one more time, because the coefficient of sine here is a 1. It, the fact that the period changes doesn't matter. the value of y still goes between 1 and -1. It will have reached its maximum at pi over 4 actually here, and it will have reached its minimum at negative pi over 4. The values of y are also bounded, so the range of y is between -1 and +1. And finally, the overall shape of the our parametric equation will look something like so. You can use your calculator and have a play around with it and figure out that it will look like so. Let's look at the final example here. So a curve has parametric equations of cot t plus 2 and y is cosec square of t minus 2. T is bounded between 0 and pi. We are to find the equation of the curve. Well, it doesn't state that it's a Cartesian equation, but f of x means that it has to be different in terms of x. So we're going to look at some of our previous knowledge of what we found with trigonometric identities here. So cot is x minus 2, cosec square is minus 2 can be rearranged so that we will get cosec square on one side. And if you remember what's the definition of cosec square, uh, if you remember this identity we came across in chapter 6, this was basically, if I jog your memory, sine square plus cos square, that was equal to 1. So if we divide both sides of this identity by sine square, what we get is this identity here. So dividing every term there by sine square. I encourage you to do that for yourself and you will come up with this equation. So what it means is that we have y plus 2 here, and instead of cot we will use x minus 2. So we'll have 1 plus open square bracket here, because cot is a square, we'll have x minus 2 there squared. Okay, so finally we subtract 2 from both sides. I'm gonna flip the equation from right to left so it'll be easier to read. X minus 2 inside the bracket here plus a 1 minus 2 will give us a minus 1 here. So y is x minus 2 square minus 1. So you can use the, well, we can further expand this bracket if you wish, but to plot this curve answer part B here, we have to sketch this graph. We know that its minimum is, this is in completely square format. So the curve will have its minimum at x equals to positive 2. So just take this bracket, set it equal to 0. You get the minimum point or turning point of x is at x equals to 2. So that's the turning point. Now we want to know exactly where it crosses the x and y axis. If I expand the bracket there, I'll have x square minus 4x plus 4 minus 1 plus a 4 minus 1 is a plus 3. Now, if we factorize this equation, we'll have x minus 3 and x minus 1, and setting it equal to 0, that tells us that the roots of the equation are 1 and 3. Therefore, I know that this graph will cross the x-axis at 1 and 3 here. We already figured out its minimum is at 2. And where does it cross the y-axis? So to figure out the y-intercept there, what we can do is set the value of x equal to 0, because x equal to 0 on the y-axis, and that would give us minus sorry, that was a plus 3 there. So that would give us a positive 3 for the intercept. Every time you are asked to sketch a curve, you yes, you don't have to be accurate, but you do have to point out where the intersection points are with the x and y axis. So make sure you do give the intersection points as I did over here on the graph. Okay, so happy practicing. I'll see you in the next video. In this example, we are not explicitly asked to calculate the range of values for x and y, but it's important to always the range of values and consider the fact that t can only vary between 0 and pi. So considering the fact that x is cotan of t, we can plot the graph for cotan of t, which is the 1 over tan. So basically, the plus 2 there is translating the graph of cotan by up by 2 values. So let's look at the graph of cotan here. We have x value that its range will be entirely from minus infinity to positive infinity, because you can tell the x is on the y-axis here. So don't what we are saying is that this I know we know that the asymptote of cotan is at pi and 0, but so the value of x actually shoots up to positive infinity as t gets closer to 0, and x will shoot up to negative infinity as t gets closer to the value of pi. And the fact that this translation by 2 doesn't change the value. So what I'm saying is that when we are considering the graph of this quadratic here, we know now that x can take any real value.